Hello. So this is our project 2 presentation on the problem electric vehicle routing problem. In this problem, we have different constraints and we are going to solve this problem by different methodologies. The group members include me, Shivam Pandey, Divyanshu Singh, and Aditya Vilas Rao Bhagat. Let's start. So the abstract. EVRP extends classical vehicle routing problems by incorporating battery and charging constraints for electrical vehicles. Here we present a multi-objective model that minimizes the average travel time and energy consumptions per vehicle. In the algorithms, we have compared the A star search, the nearest neighbor heuristic, and the Tabu search, which is a meta-heuristic algorithm. And we have also evaluated the solution quality and its computational efficiency later in the results and conclusion section. So, in let's start with the introduction. The electrical vehicles reduce greenhouse gas emissions and fuel consumptions. And these routing EVs, since routing EVs is complex due to limited battery range and charging requirements, the EVRP problem extends the classical vehicle routing problem by considering different constraints like the energy constraints and the charging stations availability. EVRP aims to balance the travel time with energy efficiency. So the problem statement that we dealt with was to determine the optimal route for a fleet of electrical vehicles to serve customer efficiently. Here we had many different electrical vehicles in the route, and we must account for different constraints like the battery constraints and the charging stations visit. Also, we did the multi-objective optimization that is needed to minimize both the average travel time and average energy consumption per vehicle. The challenges included the battery limits, the charging station availability, and we have to balance the trade-offs between the travel time and energy consumption. The following assumptions were made during the project. The road network is modeled as a weighted graph, and the nodes were represented. The nodes were the representation of customers, the depots, the charging stations. Then there were edges that represent the travel time and energy consumption. And each EV starts with the fully charged battery of 100 units normalized, and the minimum battery level must remain above 15% of capacity. As if it goes below that, then it needs to be charged again at the charging station or return to the depot. Vehicles can recharge at any charging station during the routes, and the charging station waiting times are included in total travel time. The methodology overview, we have compared the three algorithms for solving the electronic vehicle routing problem. The A star search, which is a heuristic algorithm, the nearest neighbor heuristic, which is a simple heuristic, and then we have a meta heuristic algorithm called Tabu search. Each algorithm is evaluated based on its effectiveness, that is its solution quality, and its efficiency, that is its computation time. Then the optimization criteria that we have taken into account was the multi-objective optimization focused on two key goals: the minimized average total travel time per vehicle and the minimized average total energy consumption per vehicle. So why we have used the multi-objective? Since the faster routes, they have higher energy consumption. Then secondly, we have energy efficient routes. They took a longer travel times. And in the real world, also in EV logistic, there is a demand of a balance between the travel time and the energy efficiency. So a multi-objective approach catches these all critical trade-offs and makes the solution more practical and realistic. So from now, my friend Shivam will take on from here to explore the algorithms further.
Hello everyone, I am Shivam Kumar and now I am going to uh, walk you through a search solver AV routing problem, how we are going to optimize these things. So you all are aware what the problem we are facing as the web discussed with you. So here we are using multi-objective, multi-objective because more than one objective we are going to use to resolve this routing problem. So as we know, faster routes take high energy consumption, and energy efficient route take longer time uh, to travel. In the real world, EV's logistic demand a balance between this travel time and energy efficiency. A multi-objective approach captures this critical trade-off, making the solution from practical and realistic way. So, A star is the best first graph search guided by the heuristic. As you know, we take the local. Uh, we are going to use the local search. You guys are most familiar about the A star search. It's a heuristic based search where the each state represent the vehicle location and the remaining battery. handle this double objective using combined cost functions or multi-criteria such a strategy we are going to use. So here we are granted that the optimal solution for the small scale instead, but for a large scale it may take much time to consume to execute, or there is some limitation also become the computationally expensive time and memory for the larger size problem. So for the smaller size routing problem, ASR is one of the best algorithm. So how we are going to implement, so we are going to deep dive in the details. Heuristic optimistic estimate the time and energy destination. Cost function can be the weighted sum or apply the multi-objective dominance for the cost. Find the optimal route, include the necessary charging spots. Here, one limitation is also becomes infeasible for the larger scale problem due to the status space exploration, as I discussed earlier. So here is the mathematical model which we are going to use. We are trying to minimize the average time and average energy. Our in fact our main objective is to minimize the average time travel or average energy consumed by the vehicles. Here, let's say we are taking the n number of EVs. Each EVs have the maximum battery capacity is 100 unit. In the starting, we are assuming that all EVs have 100 unit, and the minimum battery level is 15 unit. The our objective is we are taking the average time. Average time is time taken by the all EVs divided by all number of EVs. So subject to EI is minimum of EIT and EI max. So uh, now we are going to perform this all things by the nearest neighbor heuristic, which my teammate is going to explain you the Divyansu Singh. Divyansu is going to explain this nearest neighbor heuristic. Thank you.
Hi, I'm Devanshu. Let's talk about the next algorithm, which is nearest neighbor. So, nearest neighbor is a heuristic algorithm which is greedy in nature. So, what it does, it always selects the nearest unvisited location. Few advantages of nearest neighbor is it is very fast and it is very simple, and it always produces feasible routes quickly. One of the major limitation of nearest neighbor is its myopic decisions can lead to suboptimal global solutions. It is also commonly used as a baseline for generating an initial solution. Now let's talk about the implementation of nearest neighbor. So first let's talk about its movement. So what it does, at each step the vehicle moves to the nearest customer or charging station. Now the choice of moving is totally based on vehicle's current battery range. Talking about its decision process, so it utilizes a greedy algorithm and it always focuses on local information such as distance or time or any other factor which we are considering. Now, few potential drawbacks can be, as we are using greedy, so greedy choices may lead to detours, and detours can result in increased overall travel time or energy consumption. Now, let's talk about our next algorithm which we are using, which is Tabu search. And Tabu search is a meta-heuristic algorithm. So let me give you an overview of the algorithm. So what Tabu search does, it follows an iterative improvement algorithm that uses a tabu list, which is a sort of memory, to avoid repetitive moves. Okay, so its starting point is it begins with an initial solution, which is commonly generated by the nearest neighbor heuristic. For an example, now it's exploration process. So it explores neighboring solution through local modifications such as reordering visit sequences, swapping segments of routes. Few key advantages of Tabu search is it temporarily forbids recent move to avoid cycling. Second is it helps escape local optima for improved solution quality. Now let's talk about the implementation of Tabu search in detail. First, if I talk about the evaluation strategy of Tabu search, it considers combined or separate objectives. Like in our question, objectives are travel time and energy. Talking about its exploration mechanism, it always selects best neighbor, even if it's worse, to escape local optimum. Now let's talk about the tabu list usage, which is a memory that we are using. So it prevents immediate reversal of recent moves. Next is its search management. So it continuously track the best solution throughout from a node. And a few practical advantages of tabu search are: it is flexible, scalable, and adaptable to problem specific constraints. Now let's talk about qualitative comparison of all the three algorithms. So first we have A star algorithm. The pros of A star is its optimal solution. It's explicit constant handling, and the con of A star is it is exponential. It is very computationally expensive, and it is good only for small instances. Talking about nearest neighbor, pros are it is very fast, simple, and scalable. Cons are suboptimal, myopic, poor for large problems. Talking about Tabo search, so its pros are it is close to optimal, it is scalable, it is flexible. Talking about cons, so no optimally guaranteed. So it may generate the optimal solution or it may not generate the optimal solution, but it will always try to be near the optimal. And parameter tuning is needed in Tabu search. Talking about the experimental setup, so first we have test scenarios. We are using multiple CV, customer location, and charging stations. The vehicle constant, each EV starts fully charged and must reach destination with possible recharging en route. Talking about the evaluation metrics that we are using is average travel time, average energy consumption, and the whole computation time. And the comparative analysis is basically algorithm tested on both small and large problem instances. Now, Adi will walk you through the result part.
Hi, my name is Aditya Vilasra Bhagat, and in this slide, we are going to explain about result in a small case scenarios. In this setup, we have 5 vehicles and 10 customer location. In that, we have the performance summary for 3 algorithms that we use in this project. The first one is A-star algorithm. A-star algorithm finds the optimal routes for the small scale scenario and has the lowest travel time and energy consumption and has the slowest consumption time. And the other algorithm, which is nearest neighbor, in the nearest neighbor it has 15 to 20% higher travel time and energy compared to like more than A star and faster in computation because it takes like the info really easily. And in third algorithm, which is Tabu search, in Tabu search it achieves a result within 5% of A star after moderate iterations, and computation time between A star and nearest neighbor is kind of similar. So moving on to the next slide, results for larger scale scenarios. In the setup, we have 50 vehicles and many customers and charging stations. So in that, there is 3 algorithms again that we comparing the result with. So first is A star. A star infeasible in the large instance but terminate due to the memory and time constraint because A star cannot take a larger input. And in nearest neighbor we have like a really good solution quality and significant degrade because it actually has the 30% worse than optimal result. But in Tabu search it maintains the near optimal solution, demonstrates stronger scalability, and offer practical balance between solutions quality and the computation efficiency. Moving on to the next slide, there is a result visualization. So in the first figure, we can see there is a bar chart for the 3 algorithms divided in energy, time, and distance. And the other one is just like the plot chart, but it has like the same comparison, but like it's the same charts. So in smaller cases, A star usually gives optimal and near optimal results. Tabu perform closely, especially with good tuning, and nearest neighbor tends to lag behind. If Tabu outperforms here, it might be due to better parameter tuning or different object to awakening. Moving on to the next slide, there is a discussion. So in discussion, we can discuss about trade-off between optimality and scalability. So A star is optimal but impractical for larger problems. Nearest neighbor is fast but loses quality within problem size, and Tabu search offered a practical balance for real-world EVRP. In A-star algorithm, it's best for smaller problems but not scalable for the bigger ones. and nearest neighbor, which is an fast but poor quality as problem size increases, and Tabu search balances quality and efficiency, suitability for larger instances. Moving on to the next slide, there is possible future scopes. So in the possible future scope, there is hybrid algorithms. Hybrid algorithm, which is combine A star for subproblems and also use Tabu or genetic algorithms for global routing. So this kind of hybrid algorithms can enhance the performance, and additional objectives can consider charging cost or customer time windows, and real-time online EVRP gives you dynamic routing as conditional charging. Integration with EV infrastructure can also give you better routing solutions, and advanced techniques uses the Metaheuristic and machine learning for further improvements. Moving on to the next slide, there is a conclusion. So, multi-objective EVRP requires balancing travel time and energy under battery constraints. A star is optimal for smaller cases only. Nearest neighbor, faster bird, suboptimal, and Tabu search near optimal and scalable. Heuristic, meta-heuristic approaches are practical for EV routing and provides a foundation for further research and sustainable EV logistics. So that's just the references that we use to do this project. And thank you so much for listening to us, guys.